Introduction to symmetrical components. In power system, if the fault occurs, then the system becomes an unbalanced system. Okay, so it is proved that unbalanced system of n related vectors can be resolved into n balanced vector. That term we call it as a symmetrical component of original vector. Symmetrical component is the unbalanced system of n related vectors can be resolved into n balanced vector. This term we call it as a symmetrical component. Balanced system in the sense the system is subjected to a fault. A power system is there. If in the power system, if any fault occurs, a lightning occurs or any short circuit occurs, single line to ground fault occurs, during that time the system become unbalanced. Okay, normal working condition is a balanced condition. Okay, so this symmetrical component will come under the unsymmetrical condition or unbalanced condition. Unsymmetrical is nothing but unbalanced. Both are same. So we are going to convert that unbalanced system into a balanced system vector using this symmetrical component. So here you can see these are the symmetrical component. One is positive sequence component, negative sequence component and zero sequence component. So these are the three symmetrical components. So under balanced system you can see your phase current, A phase current plus B phase current and C phase current, this will be equal to neutral current and that will be equal to 0. So if you add all the three phase current, then that will be equal to neutral current and that will be equal to 0. This is under balanced condition. And in unbalanced system, this will not be equal to 0, since in any one of the phase of fault occurs, in A phase fault occurs means then the system get disturbed, the current value will be somewhat different. Okay, so that this 3 current will be equal to IN alone and it is not equal to 0. This is the two conditions for balanced and unbalanced system. So now the positive sequence component. So here the unsymmetrical, the symmetrical components are these three: positive, negative and zero sequence component. And first the positive sequence component will be so like this. So here you are considering the A phase current IA as a reference, taking this as a reference phase. Okay, draw one line like this, IA plus. Okay, and this side IB plus and IC plus. These three phase currents are 120 degree phase displaced. Now under positive sequence component, this IA, and you are rotating this sequence in clockwise direction. So positive sequence means you have to rotate the sequence in clockwise direction. Okay, while you are rotating this sequence in clockwise direction, taking this IA as a reference, you can write the equation as IA plus is equal to IA plus angle 0. Why I am putting angle 0 means it is a reference one. With this reference IA plus, I am going to write IB plus, that is second phase. See the diagram. IA plus is a reference and I am going to write IB plus now. Okay, so what is the angle difference between this IA plus and IB plus? It's minus 120 degree. Minus 120 degree you can put, or plus 240 degree in this way. Okay, so IB is plus 240 degree. So IA plus is a reference angle, plus 240 degree is nothing but IB plus. Similarly for IC, if you write, IC is 120 degree. So from IA is a reference, directly you can come here, IC is 120 degree. So IC can be written as IA plus angle 120 degree. So now we are going to introduce an operator A, okay, for representing this angle. This operator A will turn a phasor through 120 degree in three phase problems. So instead of making a 120 degree, 240 degree, so like that you are just replacing that with the term A. Okay, so wherever 120 degree comes, you can just replace with a small a. Okay, this is to reduce the complexity in the calculation. So instead of 120 degree, I am just replacing a, and 240 degree replacing with a square. Okay, and you have to note down these things. A for 120 degree and a square for 240 degree, and a cube is equal to 1 and a power 4 equal to a, 1 plus a square equal to 0. So now next one, the negative sequence component. So here is positive sequence component, we are rotating the sequence in clockwise direction. Okay, now in the next one, it is the same thing, we are rotating in anti-clockwise direction, that's all. And writing the current value as IA minus. IB minus and IC minus to represent it as a negative sequence component. Okay, so anti-clockwise direction, IA minus is the reference, so you can directly write, and IB minus. So IB minus in the sense it is clockwise direction, so IA as a reference, IB is 120 degree phase displaced, so you will be getting IA minus angle 120 A into IA minus. Similarly for IEC, anti-clockwise direction, so you will be having 240 degree, so IA minus 240 degree, that is A square into IA minus. Okay, then third one is a zero sequence component. All the phases are in phase with each other. IA, IB and IC are in phase with each other, so there is no angle difference. So all the values are same. IA naught is equal to IB naught is equal to IC naught. Okay, so these are the three phase sequence components.